the Chinese diet of the 80s, for example, or the Japanese diet. They're very low in sugar. There's other things that are obviously different about their diet and our diet, but sugar is a very conspicuous one because the Western diet is much higher in sugar than those other traditional diets. Thanks so much. I think it's because I approached it from a different angle. I didn't actually mean to write a book about cancer. I've written a lot about sort of weight loss. So as a kidney specialist, I deal a lot with type 2 diabetes, which is related to obesity. So I deal a lot with sort of metabolic health and that kind of issue. And one of the things that was sort of on the periphery of that was cancer. So as I started to look into that relationship between obesity and cancer and type 2 diabetes and cancer, the story just got more and more sort of fascinating. And it's super interesting to me because it was actually nothing that I had learned before, because I went to medical school in the 90s, and the entire relationship between obesity and cancer and type 2 diabetes and cancer really wasn't sort of fleshed out until the mid 2000s. And a lot of the new data on the change from the genetic paradigm of cancer to this more evolutionary view of cancer was also brand new, sort of in the last 10 years or so. And it was all sort of like new to me. I hadn't sort of appreciated sort of the massive change in the way that, in our understanding of cancer. It doesn't change sort of cancer management and so on, but it was sort of just this really, really fascinating sort of understanding of what cancer is, how it develops, because that's something that we've never known. Like, what is this strange disease of cancer, right? It's completely different than any other disease that we encounter, and yet it's the number 2 killer of Americans. So, like, if you look at heart attacks, for example, like, we know what causes heart attacks. You get a clot in an artery, a blockage in an artery, you get the hardening of the arteries, you get heart attacks. We know what causes infections, like, there's bacteria cause infections. We have viruses like COVID, other diseases like ulcers are caused by other bacteria. So we've sort of figured out a lot of these diseases. We have genetic diseases like sickle cell anemia and so on. So we've sort of figured out what causes these things. But cancer is such a fascinating disease because it's a disease that comes from ourselves. That is, if you have lung cancer, that lung cancer cell developed from your own normal lung cell. So why? Why would it do that and kill you? And it's not some rare disease that we've never heard of or ever seen. We see it all the time. So for such a common disease, we really had no idea of what is going on. And most people don't know. And I'll bet that most doctors also don't know about this sort of changing understanding of what it is. And to me, it was such an interesting shift in the last 10 years because it explains so much of cancer medicine that we could never explain. That is, if it was a genetic disease, why is it so common? Right? Why does everybody get cancer? Why does every cell in your body have the potential to become cancerous? Why does every animal in the animal kingdom potentially have cancer? Like, why is it? It's clearly tied into something very deep in our evolutionary past. But, to put it all together was just so, to see it sort of the science unfolding and so on was just so interesting. So, I'm not sort of a cancer researcher. I'm just sort of trying to put the story together for people to understand, to sort of appreciate what this disease has changed in the scientific view, and the implication of that to how treatments are now progressing. That is, we've sort of moved a little bit away from trying to fix these genetic changes, and we're trying to tackle it as an evolutionary disease that is using things like immunotherapy and adaptive therapy and all these new sort of modalities of cancer medicine that are just so promising. So it's just trying to understand this disease. But to me, it's sort of the greatest medical mystery there is. And just to have a better understanding of it is just so so interesting.
Yeah, and I love this. You even bring out some stories that have a parallel with yours, which is bringing out some outside perspective for cancer research. They recruited some physicists at one point. We'll talk about that hopefully a little bit later. But you having a different perspective, a different paradigm is so valuable because you're able to look at this from a new dimension. What we tend to see is we end up with scientific tunnel vision. And when things are kind of commonly accepted as true in medicine, we have to fight really hard. And you've got multiple stories throughout the book as well about paradigms with cancer and new research affirming things that are factual, taking decades to change. But you also take folks through a little bit of the history of cancer to start out. And can you talk a little bit about that? Because cancer has been documented throughout the long history of humanity. This isn't a new thing.
Yeah, it's a really interesting thing that we've actually seen cancer even sort of as far back as we can find. So you can, in the fossils and so on, you can find ancient humans and ancient Egyptians in the writings. They've talked about cancer. Now it's a very rare disease because we know that cancer is a disease that tends to increase as you get older. And of course, life expectancy was much shorter, but it wasn't unknown. So one of the things that people often say is, "Oh, we don't know what causes cancer," and that's actually completely untrue. We know a lot about what causes cancer. In fact, you look at things like smoking. We know smoking causes cancer, right? We know that certain viruses cause cancer. We know that there are genetic things that cause cancer. We know that asbestos causes cancer. So there are many, many things that we know cause cancer, and those are called carcinogens. And there's a huge list of these carcinogens. You can find them on the internet. It'll probably take you 3 seconds on Google to find the World Health Organization and other organizations maintain these lists of carcinogens. So it's not that we don't know what causes cancer. We know lots about what causes cancer. It's how that sort of, smoking or asbestos or so on, how that carcinogen leads to the development. That's the sort of part of the puzzle that we hadn't quite figured out. How that sort of moves from smoke, tobacco smoke or asbestos, to lung cancer or to mesothelioma or whatever. And that's where the science has been in the last little bit. One of the things that's super interesting is that in the sort of 80s, 70s, and 80s, they started to look at what are the most important causes of cancer. Smoking was actually the number one, and diet is actually number two. So 35% of the attributable risk of cancer is attributed to smoking. So 35 for smoking and about 30 for diet. So huge, like a huge impact, and far dwarfing anything else like radiation and, chemicals and pesticides and all the other stuff that we worry about. And we do so rightfully, but diet was this huge factor, and that's sort of been untouched because there's all this debate about diets and again, the new science of the last 10 years is just starting to unravel the link between diet and cancer. So that's,
Yeah.
another interesting
Well,
thing.
that's the thing too, is that you go through all the different paradigms throughout the book of what we believe cancer is and where it comes from. And I think it would be really helpful right now is to, number one, because we've talked a little bit about what causes cancer, but what is cancer? If you can give us a summation of what cancer is, and then let's talk about some of these paradigms, because we've gone through multiple paradigms, and one of the big pieces that came out not too long ago are these kind of hallmarks of cancer as well. So let's talk about that.
Yeah, so the if we go back to sort of the 1940s, so these are the modern paradigms of cancer. There sort of are three big ones. So we started off and what I mean by paradigms of cancer is what we view as what cancer is. So the first sort of major paradigm was cancer is a disease where the cells just grow too much. So the point is that if it's you have a lung cancer cell, it's growing all the time. So it's dividing, it's spreading, it's metastasizing, so it's just growing too much. And that's what kills you in the end. If it grows too big, it'll, damage other organs. If it spreads around all, to the bones and to the brain, it will grow and damage the normal tissues. And that's how cancer often kills you. And this idea that it's a cell that grows too much is it's I'm trying not to be trivial. It sounds very basic, but it's not that basic. This is the 40s, and what the paradigm is, why the paradigm is important, because it informs how you treat it. That is, if this is a disease where the cell grows too much, well, then the answer is kill it. So that was the basis, that formed the basis of all our modern treatments for cancer. So if you look at surgery, it's a way to cut it out. If you look at radiation, it's a way to burn the cancerous cells. And if you look at chemotherapy, which was the big sort of advance in the 40s, it's basically a selective poison. So you're trying to kill by poison the cancer cells a little faster than you kill the normal cells. So it's a selective toxin. That's really all it is. These are just ways to kill cells. And that's because your paradigm, the way you view cancer, is that it's a cell that grows too much. It doesn't tell you anything about why it's growing too much, but it's a valid way. And of course, it was a huge advance. So if you look at the chemotherapy through, the cancer, there was very little treatment before the 1940s. We started to develop these chemotherapy drugs, in the 40s and 50s and 60s. And then the major advance was combining the chemotherapies in different regimens. So now you start to say, okay, let's use this plus this and this plus this or this, and then we'll give it 3 weeks, do it again, and then do this and do this. So it was just a way to sort of refine our way of killing cells. So we'd say, oh, let's do surgery and then chemo, or then surgery plus radiation plus chemo. And we did all these trials, and it was a huge success for its time. So it took cancer from sort of no treatment to some very successful treatments. A lot of the pediatric cancers, for example, very high cure rates. But the main cancers that affect people, the things like breast cancer, colorectal cancer, unfortunately didn't do as well, but a huge advance. And that took us up to about the 60s and 70s. And the next big sort of paradigm shift in cancer came with the advent of the genetics revolution. So we started to understand that, hey, the genes in our cells actually are what's telling us cells to grow or to not grow. So if you have a genetic mutation in a cell, and that gene mutation is a critical area that affects cell growth, well, you could get excessive cell growth. So this paradigm that these are genetic mutations, genetic changes, which are affecting growth, doesn't invalidate the first paradigm. It's merely trying to build on it. That is, we accept that cancer is a cell that grows too much. But why is it growing too much? And that's the next great paradigm shift. It's a genetic mutation that causes the cell to grow too much. So you're not trying to say, oh, that was wrong and this is right. We're just trying to say, okay, let's expand our understanding. And that's what science does best. So we started to find these genetic mutations, and then they discovered in the sort of early 70s, 80s, these oncogenes. So these are genes that control growth. And sure enough, when you started to look at cancer cells, you could find these genetic mutations. So that was a huge, huge validation of this genetic paradigm of cancer. And that's sort of where we've been from the sort of 60s, 70s, all the way to the 2010s. So the first few treatments were super, super successful. So there's two drugs, one called imatinib for a type of leukemia, and another called trastuzumab, which is Herceptin for breast cancer. And these were great drugs because they were not drugs that were designed to kill cells. So it's not like chemotherapy, oh, we tested it, we killed a lot of cells. this was a drug that was designed to fix those genetic mutations. So in imatinib, which is the first sort of great drug, um, we identified the sort of problem genetically, and this was a drug that fixed it. And when it did so, it completely changed the life of these people. Like, it was practically curative. Like, people went from sort of a death sentence to a relatively normal life with this one pill. It was just incredible. So in Time magazine had it on its cover. That was how important this was. Herceptin, which is trastuzumab for breast cancer, was similarly just a fantastic drug. It was so they identified these mutations called HER2 mutations, and they recognized that not all breast cancers had this mutation. So if you gave this drug to everybody and only 20% of people had this mutation, well, you're treating 80% of the people that are not going to benefit. So in another huge advance, they said, well, what we're going to do is design a test to see if you have this mutation. And if you have this mutation, then you give the drug. So that's great because you've got this expensive drug with a lot of side effects, but you're only giving it to those people who are going to benefit. So that ushered in the sort of era and the promise of personalized medicine. That is, the drug that we give person A is going to be different than the drug we give person B based on a test that we can do to see what kind of breast cancer they had. So not only genetic treatment, which was huge, but personalized medicine. So personalized, targeted medicine. So by the 2000s, we had these two drugs, and that was like it. Like we are on the verge of curing cancer, boys. Like, that is how optimistic we all were. Like, we thought this was just going to be done. So by the 2000s, we started talking about the Human Genome Project. And so the idea was you'd map the genes of a full human being. And remember, at the time, I mean, it took like 5-6 years. It took hundreds of millions of dollars. I mean, I think you could get it done in 24 hours right today, right? But at the time, it took a long time to do this. And in 2000, it sort of finished. The Human Genome Project finished, and we said, okay, well, that's it. All you have to do is look for this type of cancer. So breast cancer, you have these 3 or 4 mutations, find the drugs. Colon cancer, find these 2 or 3 mutations, find the drugs that are going to cure them, and you're going to cure every single type of cancer. That's what we thought. That's what we really believed. We were on the sort of precipice of a cancer-free world. But unfortunately, it didn't turn out that way. That is, those first few drugs were still the best. They were basically, if you look at the number of drugs that came after that were that successful, I don't know if we've replicated it since. So in that sort of 40 years of the genetic paradigm, we had 2 great drugs, and then now, like, if you look at the number of drugs that have made a significant difference, it's probably like you could probably count it on one hand. That's not a lot of progress. And if you look at what happened to that story of, hey, cancer is this 1 or 2 or 3 genetic mutations in a critical area of the gene, and that's causing it, we fix it and you're done. It didn't work out. Because as we started to get the technology, we did this Cancer Genome Atlas, which was a big project. So instead of mapping the genes of one human, we mapped 33,000 cancer samples, and we did the full genome of all these cancers. And then we were going to take, say, all the colon cancers, match them, and say, okay, these are the 3 or 4 critical genes. When they did that, what they found was not 3 or 4 genes that were mutated. I think, at the last count, it was something like 6 million genes.
Hold on. 6 million different gene mutations are linked to cancer.
Exactly. It was crazy. So they'd have this database called the Cosmic Database, which was this worldwide database of all the gene mutations of cancer. So if somebody has a cancer, they map the genes and they say this is it, and they put it on the database. And it was complete bedlam. So even by the mid-2000s, 2010, what you could find is that if you take one colon cancer from patient A, it's not that he has 2 or 3 mutations. He probably has 50 to 100 different mutations in various genes. And if you look at the person next to him in the cancer clinic or the person next to her, they would have 50 or 100 mutations and completely different than patient A. So it's like this is going to be a huge problem because you can't treat somebody with 50 drugs. We don't have that many drugs. And the other thing is that you could use 50 drugs on patient A and you need 50 completely different drugs for patient B. It's a complete mess. Like, you can't develop 6 million different drugs. It's just an impossible task. And that's why the sort of progress in cancer came to a screeching halt, because this paradigm, because we had already reached the limits of paradigm one, right? There's only so many ways to kill cells without killing somebody. It's hard to do, right? Chemotherapy, new drugs. So then the genetic paradigm was much less toxic than these other drugs. But the problem was that there's just too much variation. And the whole the whole problem is that if you looked at the progress in cancer medicine, there was very little progress compared to the rest of medicine. So, for example, heart disease. So I compare heart disease and cancer a lot because they're the number 1 and 2 killers of Americans. And if you look at the 1960s and 1970s, you're sort of twice as likely to die of heart disease than you were of cancer. But the progress in heart disease has been quite steady. So you look at death rates from heart disease, they've been actually trending down slowly but steadily as you have better drugs and better procedures and better technology and less invasive this. And their mortality from heart disease has been steadily going down, but cancer has stayed relatively flat. And therefore, the rates of death from cancer and heart disease are about the same. So you went from something which killed twice as many Americans, which, heart disease killed twice as many as cancer, to almost the same, which means that relatively progress in cancer medicine has been very, very slow. In fact, if you look at sort of survival after breast cancer, colorectal cancer, that survival hasn't gone up a lot in the last sort of 30 or 40 years. The treatments just haven't kept
A
up.
big part of that looks like a big part of that in your research obviously is attributed to getting stuck in a paradigm where we're focused on these gene mutations. And then once this was actually mapped out, seeing that this was far bigger of an issue than what was once thought about. Now, what I would like to do, which is so wonderful, you highlight these throughout the book, is what are some of the causative agents behind gene mutations in the first place, and addressing these, which this is still kind of pruning the edges, but still this is an important thing. So some of the things, when we think about a gene mutation, we think that it's just a haphazard, like if there's this imminent gene mutation that's going to cause cancer. When a lot of the cases, that's a very small percentage that it just happens on its own. You mentioned this term earlier, and I want to dive in deeper here. You mentioned the term carcinogens. And so these are cancer-causing agents. These are things that effectively contribute to these gene mutations that can lead to cancer. And you mentioned this, and I do not want to bypass this. This is one of the times I had to put the book down and just think about it for a moment, how crazy this was. And one of those carcinogens really early on that was identified was asbestos. And you talked about the story of Dr. Leroy Gardner and his research around asbestos. And unfortunately, the suppression of the data for about 40 years and the connection with mesothelioma, that form of cancer. Can you talk a little bit about that, these carcinogens? In particular, let's talk about asbestos a little bit.
Yeah, asbestos has been used for a lot of years. So you can find mentions of it in sort of ancient Rome and so on. And interestingly enough, they knew it caused a lot of lung disease because the workers in those asbestos mines, they would often get lung disease. So they were not doing so well. However, it became one of the sort of important materials of the industrial age, because as we started to build these great big engines and we had coal fired this and powered everything, the big risk was fire, especially on Navy ships. So as you got to World War II, people started using asbestos everywhere because it was fireproof. That was the main thing. You had this light material that you could weave and you could make it fireproof. And that was great because if you're designing something where there was going to be a big engine, then you could, make it fireproof. You can improve the safety of it. And that translated into the home. So they took that technology from World War II Navy ships and they basically said, well, we're making all this asbestos. The war is over. Let's put it in the homes. Um,
Okay.
because, yeah, it was sort of one of these things nobody anticipated. But of course, you know that if you buy a home from that, prior to the 1960s or something, there's a good chance it could have asbestos in it, and you have to go and get somebody to take all the asbestos out. Like even now, if you buy a house, you need to be aware of that. It's actually one of these things, and the real estate agent must disclose. Like it's by law, you have to know about it because it's such a dangerous thing. But anyway, so because this was such a great fireproofing material, it wound up in all the HVAC sort of areas of the home, sort of the heating and cooling, because you had a furnace and you didn't want the furnace to catch the wood that the house was built on. You didn't want the wood to catch on fire, so you'd wrap it in asbestos and all this stuff. So almost all the houses built in that era prior to us knowing about it showed that asbestos was there. So Dr. Gardner, but there was this sort of lingering doubt about asbestos and cancer. It caused this cancer of the lining of the lung called a mesothelioma, and there was some worry that asbestos could cause this cancer. So they hired Dr. Gardner to prove that it didn't. Unfortunately, it proved that it did. So when he gave all this asbestos to all the mice that got asbestos basically got lung cancer, this mesothelioma, and the other mice didn't. So clearly it was a problem. But he was employed by the big asbestos companies, which, there's a couple of big asbestos companies. And they basically said, look at your contract. It says that we paid for the research, we decide what to do with the research. So they basically shut it down. And they said, you can't say anything. You're contractually bound not to say anything. And it just killed him. He was like, later on, it all came out in the litigation of the 1980s.
And this was
It
in the
turned out that
1940s.
yeah, this was in the 40s because that was the World War II era, right? So it was crazy because here it was, the research that proved that it caused cancer. The big asbestos companies said, no, this research is not going to see the light of day. We're not doing it because we're putting it away, we're shutting the door, and that's it. So he couldn't say anything. And then, of course, later on, everybody found out that it did cause mesothelioma because this was a cancer that nobody ever saw before. And now you started to see it in all the asbestos workers and people who are working with HVAC and stuff. They were all getting mesothelioma. It became quite a common cancer. So from very rare to very common. And it's like, well, what's the link? And it's like, obviously, it's asbestos. So, eventually it came to light that it did cause it. And then those big three asbestos companies, they got sued. And in that litigation process, they subpoenaed all this stuff. And so it comes out that, hey, they knew about this all that long ago and just didn't tell anybody. And I don't know how many thousands of lives it cost, but it was
You
tragic. And it was all because they wanted to, preserve their business. It was
you
crazy.
put this in the book that mesothelioma in that time frame jumped up 1.5 million%. It's insane. It's
It's
insane.
insane.
And it's just, again, it's a common practice to put this stuff in our homes. And, it's just like nobody thought twice about it. People are very trusting. And one thing I really noticed in your book is the stunning amount of times that factual new insights about cancer and medicine came along throughout history, and it was shunned or even demonized by the scientific community until sometimes decades later when it's finally acknowledged as factual. And the thing is, and I know this for certain, I know you know, it's happening today still. We think we're so evolved, but we're doing many of these same practices of thinking science is definite. This is the end thing, and there's no other discussion around it. When we have very glaring things like
Yeah.
this, I remember when I was a kid and I would see the commercials coming on. Do you have mesothelioma from, call Brown and Brown and get your settlement, And now today it's just like, oh, of course, like asbestos is like a thing of the past. Nobody would ever do anything like that. But we're still existing in that paradigm. And one of the other things I want to ask you about, because there's a ranking that we have now. The IARC, for example, the International Agency for Research on Cancer, got a ranking of carcinogens. We've got we know what causes cancer. We know some of the strongest carcinogens, but then there are these category of probable carcinogens as well. That's getting a lot more data. One of those being shift work, for example. Night shift work is a class
Yeah.
group 2A carcinogen, which is a probable carcinogen, which is something that causes these kind of gene mutations that are linked to the development of certain cancers. For example, one of the things I talked about earlier in one of my books, in Sleep Smarter, was a study done on nurses who were working overnight and seeing the prevalence of like 30% greater incidence of breast cancer, for example. So again, we know so much about these carcinogens. One of the other ones I'd love for you to highlight, you mentioned it a little bit earlier, I've got to pull out from you a little bit more, is that we know that certain viruses are carcinogens as well. Can you talk a little bit about that?
Yeah, that was also a very interesting story too, and this was something sort of unexpected. That hey, viruses can cause cancer. So when it came out, when people sort of said, "Hey, viruses might be a cause of cancer," people thought it was crazy, like just crazy. They said, "No way, it's not. It's not an infection, right? We know what viruses do, and they don't. They cause, you know." Respiratory illness and they cause this and that, but they don't cause cancer, right? But then it turned out that they actually identified certain early cancers. So this fellow, in Africa, you have this Burkitt's lymphoma discovered by this surgeon, Denis Burkitt. And what he did was he sent it back to the UK, got the samples analyzed, and what they found was viral inclusion. So they found that this Epstein-Barr virus was actually causing this huge Burkitt's lymphoma in African kids, whereas this virus is actually worldwide and doesn't affect anywhere else, which is very strange. So, and they thought that perhaps it may be related to malaria, for example. But this idea that viruses could cause cancer was sort of electrifying. Now, on the one hand, it was terrifying because it means that this is a transmissible disease. You could transmit cancer from person to person. But on the other hand, you could do something and identify it. So it was this sort of double-edged sword. So they actually sponsored this big special virus, cancer virus program, and they poured a ton of money into it, and they actually didn't find very much. So by the 70s, they shut it down. It fell into this sort of disrepute, this idea that cancer can be caused by viruses. So they're like, yeah, sure, maybe a few viruses can cause a few cancers, but it's clearly not an important cause of cancer. And it sort of got shut down by the 70s. Everybody forgot about it. But then the funny part was that all these other cancers started to become associated with viruses. So, and a lot of Nobel Prizes got awarded to this. So cervical cancer, for example, got linked to human papillomavirus, for which we now have a vaccine against human papillomavirus, for example. Hepatitis B, we know, is a cancer-causing agent. Hepatitis C is a cancer-causing agent. Bacteria, such as Helicobacter pylori, which causes stomach ulcers as well, that also caused cancer, which was interesting and explained a lot of why it was so prevalent in East Asians. So when you looked at China and Japan and so on, they had a ton of stomach cancer, and people in America didn't. And it was like, why is that? Like we had no idea. We thought maybe some kind of genetics. But when those people from East Asia came over to America, all of a sudden their rates of stomach cancer just plummeted. And why is because they didn't have the same crowding and the sanitation was different. So H. pylori was much more prevalent in East Asia, and in fact didn't actually start to, the stomach cancer has been steadily dropping since the 30s. And we had even no idea why. It's just because standards of living and sanitation were getting better, so there's less transmission of this Helicobacter pylori. So both viruses and bacteria can cause viruses as well. So, these are all classified as sort of class 1 carcinogens, well-established carcinogens now. But, that was the sort of great part about the genetic paradigm, was that it sort of linked things like physical agents, so chemicals like asbestos and tobacco smoke, and viruses, because it said, hey, what's the common mechanism of how you go from tobacco smoke to a cancerous cell? And you say, well, it causes it through this mechanism of genetic mutations. And you could do the same thing with viruses. So viruses also cause genetic mutations and therefore lead to these cancer cells. So it's sort of that, for the time, it really tied everything perfectly together. And that's why it became the sort of dominant paradigm up until the 2010s, which is where sort of we hit the low point. We were sort of stuck. We had nowhere to go. And then luckily we sort of went on to this sort of new paradigm of understanding, because there were other things that caused cancer that we knew about, but we didn't know what was going on. Things like stomach acid. So when you get gastroesophageal reflux, you would get damage to the esophagus. But there's no extrinsic agent. It's your own stomach acid. It's coming back up. It's causing damage, and it causes cancer. Inflammatory bowel disease was causing cancer. So there's a lot of things. Lupus had a higher risk of cancer. So these other things that were causing cancer that we didn't know and didn't quite link to that whole paradigm. But we thought, well, it must be just a genetic thing. So that's why that genetic paradigm really took off, and everybody was sort of all in on it for so many years. Like the amount of money that went into this paradigm must have been like mind-boggling, because practically every cancer researcher in the world was following this path that, when you look at things a certain way, everything gets sort of colored by that. And you say, you're always thinking in the genetic paradigm, what could it be doing? How can you do this? And that's why we made so little progress, because it wasn't that there was no genetic mutations, it was that there's too many genetic mutations. And then you get into the next step, which is, okay, now we have to understand what's causing these genetic mutations. Because the problem with the somatic mutation theory, which is this sort of genetic paradigm, is that it assumed that these are random mutations. Because when you have asbestos or you have tobacco smoke, it doesn't cause targeted mutations to one specific gene. Like, it doesn't go there and say, okay, I'm going to zoom in on the growth gene and mutate it. It doesn't do that. So the idea was that this was a random mutation. That is, it causes random mutations, and by chance, one of them will hit the right place to cause a cancerous transformation. And that was the idea, is it's just random thing. But the problem was that this is clearly not a random disease. That is, if you look at cancer, it's a very stereotyped disease. That is, there was these hallmarks of cancer that were similar no matter what cancer you're talking about. And it didn't matter, what that you had 50 mutations on this side and 50 different on this side. They still acted the same. So clearly whatever was going on was not a random thing. So what was behind that? And that was sort of what led to the sort of newer understanding, which I found so fascinating.
So in talking about those hallmarks, if we could just touch on this really quickly, because I think it's important for us to help to demystify cancer a little bit more, with the hallmark being, with cancer being this excessive or even unstoppable growth. It doesn't have an endpoint like a normal cell, for example, having its normal cell replication, hitting the Hayflick limit, and going into senescence, where the cell has this kind of programmed cell death, effectively. But cancer doesn't do that. It doesn't subscribe to the same rules when a cancer cell develops. So can you talk a little bit about a couple of these hallmarks of cancer, what we know cancer to be? Because again, you just mentioned it. It seems like it's just this random thing, but there's so much that we do know. And for folks to be a little bit more empowered in how cancer is kind of operating, what it is.
Yeah, so it was an interesting thing because cancer had always sort of divided itself into different cancers. So there's lung cancer, and it divides based on the cell of origin. So breast cancer is this, and you have different treatments, and lymphoma is this, and you have different treatments. So I talk about this sort of fundamental difference called the the lumper splitter problem, which is an old term from Charles Darwin, actually. And it was an idea where when you're talking about species or you're talking about anything, there's two types of people: the people who lump everything together, and there's the people who split everything apart. And they give you different information because if you lump everything together, you get an idea of what makes them common, right? If you split everything apart, you highlight their differences. And cancer medicine had always been a splitter. So you split it between breast cancer and lung cancer and liver cancer and pancreatic cancer. And you treat them all as separate diseases. But you don't treat them all as one disease of cancer. So interestingly, it took until about 2000. So it was not until quite recently that a couple of researchers, very influential researchers, decided, hey, so they actually met in Hawaii at this conference, and they're talking about this problem, and they said, hey, we should really look at what makes cancer cancer. That is, forget about breast cancer and lung cancer and liver cancer. What is it about all these different types of cancers that makes them the same? Not what makes them different, what makes them the same? And so they decided, okay, we're going to get to work on it. So they published their paper in 2000 called The Hallmarks of Cancer. And they laid out sort of 6 things that they said were fundamental to the diagnosis of cancer, any cancer. And they didn't really think much of it, when they're writing about it, they say, we didn't really think much about it. They published hundreds of papers. So they thought it was just another paper. It turns out it became the most influential paper in the history of cancer medicine. And it was because they were basically lumpers in a sea of splitters. So nobody had really thought about this disease the way they had, which was, what is it that is the same about these cancers? And there's technical things like the cells, grow and they become immortal, but you can break it down into sort of 4 essential things. One, they grow. Normal cells don't grow. That is, if you have a normal lung, it doesn't just keep getting bigger and bigger until it sort of pops your head off, sort of thing, right? It just stays the same size if you're an adult. So cancer cell doesn't do that. It will keep growing and growing until it pops your head off, and that's how it kills you. So they grow. Second is that they're immortal cells. So, and this was a great book called The Immortal Life of Henrietta Lacks. Henrietta Lacks was this lady who had cervical cancer. They took her cells, without her consent, of course, because this was very early on. And those cells just kept replicating. You can just keep growing them in culture over and over and over. And they still do that now. This is like, 80 years
Rooted
later.
from her cells. There's like tons and tons of her cells being used like all the
Yeah,
time.
they just keep getting over and over. Now, you can't do that with a normal cell. So if you took my liver cell, you can't keep growing it. After a certain number, sort of like, 40 replications, it will stop dividing. And we know why. It's called the Hayflick limit, and it's controlled by telomeres, which are these little end caps on your chromosomes. Every time you divide, it chops off one of these telomeres. When you lose your whole telomere cap, the cell says, that's it, you can't divide anymore. So if you took my cell, which is non-cancerous, put it in a cell culture, and you kept growing it over and over, after a certain period of time, it would just stop, and there'd be nothing you could do. So they're mortal cells, but the cancer cells were completely immortal. So they grow, they're immortal, they move around. So cells don't move around. That is, your liver doesn't just jump into the bloodstream and go hang out with your, eyeball. It just doesn't do that. So cells are put in their place, and they're tightly controlled. You don't just move around all over the place. But cancer cells do, and that's a very strange behavior. And then the 4th thing is that they have this very strange way of generating energy that is different than normal cells. So normal cells, like we use oxygen, in a process called oxidative phosphorylation. And we generate 36 ATP, which is a unit of energy. So for each glucose molecule, we get 36. Cancer cells don't do that. Even in the presence of oxygen, they will use anaerobic respiration, which is they use glycolysis, which gives you 2 ATP plus 2 lactic acid. So instead of generating 36 ATP, which is 36 bundles of energy, you get like 2 plus lactic acid. So it's like, well, this is weird, because if you have a cell that requires a lot of energy to grow, why are you not using this form of energy generation, which gives you 36? Why are you using the 2? It's like buying a sports car and then putting in, taking out your 200 horsepower engine and putting in a lawnmower engine with like 2 horsepower, right? Why would you do that? You want to go fast, right? It's like, why are you doing that? So that's another very strange, anomalous behavior of cancer cells. So they put together those 6 plus 2 more they added in an update in 2011, and they said these are the hallmarks of cancer. And that's what sort of led to this sort of part of the process of understanding what it is that's going on in the cell. Like, how are we looking at cancer that they are the same? And that's the sort of this evolutionary paradigm which we currently find ourselves in, which again is an attempt to explain what is causing all these genetic mutations. So it doesn't invalidate that there are mutations. It's trying to explain what is causing those mutations.
Yeah, it's such an important, just fundamental insight that a lot of folks aren't educated about, especially if they have cancer or have cancer show up in their families, still not being educated about these very basic tenets. It's still just shrouded in mystery. Like, it seems so random, and it seems like we don't know what's happening, but we do. And now I think this is a really good point, because the truth of the matter is that, billions are funneled into cancer every year, medications, research, and yet we probably have effective treatments in the ballpark of maybe around 1% of them, and we've got so much that is effectively being wasted. And a big part of this is one of my favorite parts of the book, has a lot to do with surrogate outcomes and folks really kind of understanding what that means. And so can you discuss a little bit of the data on that?
Yeah, and this is the part the same as what we were talking about earlier with how companies can suppress the research that can be life-saving. And a lot of this is the same, and it stems from conflicts of interest. That is, if you have, and it's to do with who funds the research. If you have a corporation which funds research, well, obviously, they're only going to publicize the research that is going to benefit them. And they have every incentive to sort of disregard everything that doesn't. So when you do a study, as the public, we want to know, is it effective? That's not what drug companies want to know. They actually don't care if it's effective or not. They want to know, can we make money, right? It's a very fundamental difference. And there are many ways that you can structure a study that can make it seem effective, even though it's not. And these are the surrogate outcomes. So the only, when as a patient, what you want to know is, does it keep the cancer away, and do I live longer? That's what's really important. But what happens is that those outcomes often take years. So in around sort of the 2000s, the FDA, in an effort to get more cancer drugs available, decided to loosen up the restrictions a little bit. So they said, well, instead of having to prove that people live longer with this drug, with the chemotherapy that you're trying to test, we can use surrogate outcomes. And so there's something called progression-free survival, and there's other things like partial responses and so on. So that if you, for example, could show that your cancer shrank by 50% or something like that, you could then say this is an effective medication. And then you could apply to the FDA to say, approve my medication, and then you can start selling it. And you can make a lot of money. But the problem is that those surrogate outcomes don't reflect the outcome that you want, which is, do you survive longer? Which is overall survival. So that's a big, big problem because you wind up with drug companies that have every incentive to move those goalposts as far forward as they can so that these drugs look effective, even if they're not. And there's been many, many examples where this has been a problem. So, the FDA, to its credit, had said when they relaxed these, standards that, okay, we're going to let you get approved on these sort of easier outcomes on the studies, but you promise to do the good studies afterwards, right? On Scout's honor, right? That's what they said, because once it's approved, it's approved. And they said, you promised to do that and we'll be all good. Turns out that most companies didn't do that. They didn't do the studies that came afterwards. Because if you're approved, why would you spend money to do a study that might show that your drug actually isn't useful and therefore is not effective and you're going to have to take it down? Like, they have no incentive to do that. So they kept doing that. And it's the same as the asbestos company, right? If you fund the research, there's a conflict between sort of truth, scientific truth, and a corporation's sort of bottom line. So that's the conflict. And so that's why it's so important to look at who funds the research in these things. And unfortunately, almost all research is funded by pharmaceuticals, which is how you get all these drugs that are marginally effective, but they cost so much money. And it's sort of heartbreaking because it's one of the big reasons for personal bankruptcies and stuff. And this is there's already been a couple of drugs where when they did the actual study, it showed that the original drug wasn't that effective. There's so many examples where we have marginally effective drugs that people say, wow, it's a breakthrough because of this surrogate outcome. Whereas the data, the studies showing that, hey, does this surrogate outcome actually link to the outcome of interest? We know that they don't. So, we still don't understand, why are you allowing it, right? It doesn't make any sense, because
It's a common practice, right? That you outline in the book multiple
it's
times.
actually almost all of cancer medicine is like that
And so
now.
what will happen is they'll use a surrogate study, get the drug out on the market, make a few $1 billion, and possibly on occasion the FDA will catch this and then have them pull the drug after they've already racked up billions of dollars. And this, again, it's a common practice.
Yeah, it's a common practice. It's a horrible practice, but unfortunately, it's like, if you look at the data, it's clearly what's happening now. Like, there's ways to game the system when you do studies. Like, for example, if you were to say, okay, I'm going to compare drug A to drug B, you think, okay, if I make drug A, I want to show that's better than drug B. Well, if I'm the maker of drug A, I can choose what drug B is. So I can choose the worst thing, right? It's like, so therefore you can do the study and say, look how good drug A is compared to drug B. That's like, but then people will look at it, if they wanted to, and say, well, but drug B is nothing close to what we would normally use, right? So you're choosing your competitor. And that's what happens when you allow the drug company, who has a vested interest in proving that this drug works, you're allowing that person to do the study. It's like marking your own test, right? It's like, if I marked my own SATs, I'd get a perfect score, right? It's like, that's the same thing. You allow them to design the study, and it's happening to a degree, in fact, that's unprecedented, because not only do the drug company, they fund the study, but they find the people to do the study. And increasingly, when you read the medical literature, they're actually the ones writing the study in the journal. So the whole thing is basically, they're tilting the field as far as they can towards showing that this drug is effective when it may or may not be effective. And unfortunately, sort of like 80, 90% of the drugs are not much more effective than the old drug, what's available, but they cost sort of like 10 or 20 times more. So that's the sad part about it. It's a lot of people gaming the system to get to get to get sales, and it's obviously worked for
And
them.
now there's a new model as well that just came into existence pretty recently, which is the FDA itself being funded by money coming from pharmaceutical companies itself. I think somewhere around the ballpark of like 40% of their income is coming from pharmaceutical companies. So saying being able to literally write your own checks, write your own approval, like it's just getting deeper and deeper. And I'm so grateful for this conversation because literally millions of people, they invest sometimes everything that they've got to try to save their loved ones. All the money they've got, they pull out, put a second mortgage on their home. They do whatever it takes to try to save their lives with oftentimes drugs that are framed to be this potential life-saving thing. And more often than not, it's not even anywhere close to that. And you mentioned this earlier, and this is what I want to point back to. Drug costs are the single largest cause of personal bankruptcy in the United States. Like, people really don't get that. People are literally betting the farm trying to save the lives of their loved ones and themselves. So let's talk a little bit about the rising prices of cancer medications, because this is one of the biggest areas. You mentioned one that actually had really great effectiveness, imatinib. You mentioned that a little bit earlier. And the cost to the manufacturer to make, this is highlighted in your book, the cost to the manufacturer to make is estimated to be about $216 a year. The cost to the customer to get that drug is about $120,000 per year.
Yeah.
How is that possible?
Well, I think that what happened was that the drug, when it came out, was not even that
Right.
expensive. It was a few $1,000s. And when they priced it in 2000, rough in the early 2000s, they thought it was ridiculous. It was very high price for the time, but like sort of like a tenth of the cost of what it costs today. Sort of like a few $1,000s a year, not like a few $100,000 a year. But over that time, so this is the same drug. It just they kept raising the prices, and because it was so effective, it didn't matter how much it cost to make. It only mattered how much people were willing to pay for it. They kept raising the price. It was something like 5% over inflation. So even though it's the same drug, the prices just kept going up and up and up. And it's not like it's a new drug. Like, there's no new anything. It's the same manufacturing process. It's your same factory that's making it. And as competitors came on board, they didn't lower the price, because this is usually what happens when you have generic drugs. So you say you have one drug and another, and if the patent expires, another drug company comes in and they say, well, I'm going to cut the cost in half. That's how I'm going to compete at a lower cost. But the new manufacturers, when the patent ran out and made a new sort of second generation, they didn't lower the price. They raised the price. So basically they're colluding to raise prices, because they know that they could drop the price. They could drop the price like, by 100-fold. It'd still make a huge profit. But by colluding together, they would actually make a lot more money. It's right. Remember, baseball had that collusion thing a long time ago where they're basically trying to screw the players. This is the same thing. The drug company is basically colluding to raise prices. So they have this understanding that they keep the prices high. Therefore, the consumer, which is us as the public, we have no choice, because you go with manufacturer A or B or C, they're all really high priced. They're all a few $100,000. So you're screwed no matter where you go. And all of them are just making money. So if one of them dropped the price, of course, if one of them falls out of collusion, then the bottom would drop out of the market. But nobody has any incentive to do that. So the prices kept going up and up and up, and far in excess of what normal, inflation was. I always think back on that show. Remember Breaking Bad? This is such a great show, right? I mean, the whole reason he started selling crack or crystal meth was cancer
Mm.
costs. Even at I don't know when did it come out? 2010, something like that. Even in the 2010s, when that show came out, the drug costs were already so ridiculous that it was reasonable for a high school teacher to sell crystal meth to fund
Yeah,
his cancer medicines, right?
it's crazy.
It was already
Right.
believable at that time, and it's not gotten better, right? And unless people know about it and start to make noise about it, it's gonna keep happening. It's collusion. Like this whole idea of drug companies funding studies to make their own drugs look better, raising costs, passing costs off. You have all this conflicts of interest, not only within the industry, but like you said with the FDA, but also researchers, for example, when they leave research, often they go to a drug company. So they know that there's a hugely lucrative job waiting for them as long as, if you're a university professor, you don't want to rock the boat because you might be going to work for that guy, in a couple of years for a couple $1 million. So why would you go come down on the drug company and say, oh, you're such this is the wrong thing? And I always say, I didn't mention this in the book, but it's like it's such a screwed up practice, really, where drug companies are really allowed to pay doctors and researchers whatever they want. Like, there's a huge conflict of interest because it's like you can't pay a policeman. Like, if a company tried to pay a judge or a policeman or even a newspaper journalist, everybody would be like, you can't do that. You can't just pay people. But the drug company can pay the researcher however much they want. And it's usually in the 6 and 7 figures. So now you have this whole group of doctors and researchers and stuff. And I know because I'm not on the inside of academics, but I'm in medicine. I see it all the time. Like you have these people getting huge payouts. You have doctors getting free meals and free this and free that. And why would we allow that? Like as the public, like why wouldn't you just say, you know what? I don't think drug companies should be funding studies on their own drugs. Like, why would
It
you allow
just
that?
sounds obvious. It sounds obvious.
Yeah,
There's laws against these things. There's laws against collusion and price gouging, but it seems to not apply here. For some reason, for some
for
strange reason,
some
this is
reason.
acceptable.
Yeah.
Unless it takes so much for these things to come to light, and it's in the minority. It's a very rare occasion when it would happen. And so it hasn't gotten better. It's continued to get worse. And it's becoming, and I think that a big part of it is that we've come to accept it as normal. The public just doesn't kind
Yeah.
of, it's in the background. Just like, yeah, that's going on. What can we do about it? And not understanding that we're really
Yeah.
steamrolling this situation to where, again, drug costs are the single largest cause of personal bankruptcy. And it's not okay. This is not about saving lives. Like if we've got a medication that can actually save lives, and this was something that was altruistic, of course we want people to make a profit, but it's not about that. This is literally creating a situation where we're taking advantage of the public in a hideous way.
Oh yeah. And in a way that is sort of unique, that is not available to other industries. Like we don't accept it in almost any other industry, but we accept it in medicine. And it's like, why? But when you have bad medicines that cost too much, it affects every single person in this country. So why allow that? That's what I don't understand sometimes is why we allow that. And and maybe it's because you have to think about these problems a little bit, and it's sort of hidden a little bit because you get into this state where you say, oh, this is a breakthrough, this is a breakthrough. And I did talk about this, where there's been so many breakthroughs proclaimed in the newspapers about cancer, and yet cancer just kind of goes right along. Like there's no breakthroughs going on. It's just the
Right.
perception
It's a fake
of
through.
progress. Yeah, it's exactly.
So well, this
It's
is the part about your book that is the most the most affirmative and really enlightening, which is we don't have to participate so heavily in that universe. You know, again, there are some effective medications that have been discovered, but we're talking about a tiny, tiny percentage. For the most part, it's
Yeah.
understanding more so what are the causative agents here behind cancer, and let's operate at that level where it's actually effective. And you give this great analogy that I think it's just really a game changer of the seed and the soil. So let's talk a little bit about that.
Yeah, so the seed is really about the sort of the genetic changes and how the evolution is playing a role in causing these gene mutations. But there's actually a lot more to it than that. And it gets hidden by this genetic paradigm that it's sort of this genetic lottery system. But it's not, because if you think about a seed, you can have the same seed. You plant it in soil, it grows. You plant it in the desert, it doesn't grow. Same seed, different soil. So clearly the environment plays a huge role. And what we've lost sight of by looking so closely at the seed, which is the genes, the gene mutations, the evolution of it, is we forget that there are populations in the world that have virtually no cancer. So if you look at the old writings of missionary physicians and stuff, what they find is that when you look at traditional societies that are eating a traditional diet and following a traditional lifestyle, so they looked at places in Africa, for example, and compared that to the Europeans, they looked at the Inuit in the far north, and they find that there's almost no cancer. In fact, Queen's University in Ontario used to send an Arctic expedition up every year to see why these people are immune to cancer. As they became sort of, more westernized, that is, eating bread and sugar and so on,
Cheetos.
as they, yeah, as they sort of came into away from their traditional foods, away from their traditional lifestyle, turns out they weren't immune at all. They got the same cancers as the rest of us. And same within Africa. So in Africa, these missionary physicians would go, and what they'd notice is that the white Europeans would get colon cancer. The Africans, following their own diet and traditional lifestyle, almost never did. As those Africans became westernized and started following sort of a Western diet, they got cancer. So they, in fact, called it one of the diseases of civilization. Not a great term, obviously, but that's what they called it. This was back in the 60s. So clearly what they found was that there's a huge environmental component. Where you live has a huge bearing, and the foods you eat has a huge bearing. If you take a more recent example, you can look at Japan, which is a very sort of modern nation, and you can look at America, and the rates of cancer are strikingly different. So you can't say that one is civilized and one isn't, because both are civilized. But you move a Japanese person to America, and the risk of cancer goes up, way up. The risk of prostate cancer goes up, the risk of breast cancer goes up. So it wasn't about the genetics, because it's the same Japanese genetics that moved over. It was something to do with our diet. And that was huge, because if you go back to that, what we talked about earlier, which is that the sort of attributable risk, tobacco was at 30%, but diet was right behind it at 30%. So what we need to know is not more about the genetics of cancer. What we need to know is, what is it about our diet that is making us get cancer? Because that's the important thing that we can actually do something about. And it turns out that there's been a huge amount of research in the last 20 years which has looked at this exact question. And it turns out that obesity is probably one of the major risk factors. Type 2 diabetes, again, one of the major risk factors. And it comes down probably to the high insulin levels. Insulin, we think of it as a metabolic agent. That is, you give it when you have type 1 diabetes. Insulin is a hormone that goes up when you eat a lot of refined carbohydrates, for example. Insulin spikes way up. Turns out that it's a nutrient sensor. That is, it tells the body that nutrients are coming in, but it's a very highly potent growth factor. So if you put the seed, which is that sort of cancerous seed, in the soil that is highly promoting growth, you are going to get the growth of those cancerous seeds. If you take that cancerous seed and you put it in a soil where there's very low insulin, like there's just nothing to grow with. There's no growth factors because that's the soil. That's the good soil is with lots of growth factors. If you put it in a body that has no growth factors, it's going to have a lot more trouble growing. And your own intrinsic anti-cancer defenses will be able to take care of it. And that's the whole point. We have to understand not only about the seed, but we've looked at the seed for so long. We have to understand the soil. And that's where obesity, type 2 diabetes is such a huge risk factor and something that is actually completely within our control.
This is so remarkable because, so you just mentioned this with, if we're talking about the seed, we're really talking about the fact that, number one, these genetic mutations being the seed of cancer, the seed of cancer is really, I think we have a tendency to think that it's relegated to certain cells. We have the seed of cancer in every cell of our body. And that's the big thing to kind of like, it's a paradigm shift. Like the seed is there in every cell of our body. And it's not just uniquely human. This is across different species as well. The seed is there for cancer, for mutations. But the environment, the conditions are what, and so much of our paradigm has been focused on the seeds of cancer, while the soil and the conditions have largely been ignored. And you bringing up this issue around insulin, for example, and being a very powerful growth agent, this brings to light something I've got to ask you about. This is so interesting. And one of the big drivers we think about with diabetes and obesity is sugar, and a big driver of insulin activity. And the connection between sugar and cancer, funny enough, is commonly debunked, quote, debunked. But some of the most, and this is some of the most prestigious organizations claim that there's no connection, but there is, and it's not hard to find. Just talk about a PET scan, for example.
Yeah, it's, so glucose is the sugar that we use. And a PET scan detects cancer by detecting how much a cell takes up that glucose. So cancer cells take up that glucose, which is sugar, far more rapidly than any other cell around it. So it lights up like a candle. It's like just this big blob. Because you use radioactive labeled glucose, and you see what cells are taking up that glucose. So you know that the cells love this stuff. Like they're just going to town on that glucose. So you know the cancers are feeding themselves with that glucose, and yet people are saying, well, it makes no difference if you eat sugar, which causes insulin resistance, which causes high insulin levels, and so on. And it's one of these things where I find it very strange because there's a clear sort of pathophysiology. Like the science is there. It's not like it's completely UFOs did it sort of thing, right? It's
But
like
don't bring that up.
It's not something so.
Dr. Fung, don't bring up the UFOs right now. At this time, we're seeing all of these different things. It might be aliens, but anyways, go ahead. I'm sorry.
There might be aliens. Yeah, they're right with all the new Navy pictures. But you know what I mean, right? It's not that this random thing that somebody said. It's like there's clear evidence that there's something in our diet that has changed from traditional society to modern society that influences cancer rates. Sugar is one of the most common things that as you go from a traditional society, traditional diets are very low in sugar. And again, it's hard to compare, say, an Inuit diet where they're eating whale blubber and so on, but you can look at the Chinese diet of the 80s, for example, or the Japanese diet. They're very low in sugar, amongst other things. So there's other things that are obviously different about their diet and our diet, but sugar is a very conspicuous one because the Western diet is typically much higher in sugar than those other traditional diets. The Chinese people, of course, in the 80s and 90s had extremely low levels of sugar, but they've been westernizing very quickly. You look at places like Shanghai and stuff, they're huge metropolises now, and their sugar consumption has gone way up too. And unfortunately, diabetes has gone way up. So they went from sort of a 1% rate of type 2 of diabetes overall to like 10, 11%. They're actually higher than the United States, which is scary because they have a huge number of people. So it was clearly not genetics because they changed within the space of a generation. From the 80s to the 2020, that's one generation, and your rate of type 2 diabetes went up sort of like tenfold, right? That's 1,000% it went up. So clearly it's not a genetic thing, it's a dietary thing. And we know that if you have type 2 diabetes, if you have obesity, which also is mushrooming in China, then your risk of cancer goes way up. In fact, there's 13 different types of cancer that the World Health Organization has deemed obesity-associated cancers. And these are some of the most important cancers that we have: breast cancer, liver cancer, pancreatic cancer, colorectal cancer. Like, other than lung cancer, which actually has nothing to do with obesity, it's all about smoking. Those other cancers are like the most important cancers that we have. So, and they're all obesity related. All the top scientists say they're all obesity related. So if they're obesity related, then sugar is going to play a key role, because everybody knows, eat a lot of sugar, you're more likely to gain weight. If you're more likely to gain weight, you're more likely to have type 2 diabetes. So it's like, I don't know why people even argue this kind of thing. The effects are going to take decades. Cancer doesn't develop in a year. So, people do these studies and it's like, oh, we did a year-long study and we didn't see any increased risk of cancer. It's like, well, that's because your time scale's all wrong.
Right.
It's like saying, we've determined that if you put metal in water, it doesn't rust, because we put metal in water and 4 days later, it didn't rust. So we've proved it. Like, no, your time scale's all wrong. Cancer takes decades and decades to develop, so you can't see the effect right away. You can see the effect sort of on sugar consumption, for example, and obesity. We see that link very clearly. So now there's a link between obesity and these other obesity-related cancers. So therefore, the link between sugar and cancer is not really a big stretch of the imagination. Like, they're two very clearly related things. So why people bother arguing, I just don't
It's
understand.
crazy, like you just said. I think that that's a great understanding, is that when we're looking at this in this very short-sighted perspective with sugar, for example, and not understanding, it's kind of like a bamboo tree's growth. Like, there's so much happening, festering kind of below the surface before, boom, you see this big manifestation. Like with cancer, for example, now we can identify it, but it's often many years in the making when we can actually identify it. And sugar is really still, it's in the same domain as like asbestos right now, where it's taken all of this time and all of these years for it to be acknowledged as dangerous. Yeah. And the thing is, it's like, it's the shift that's taken place in our culture. Just like asbestos, there was this shift, and we've identified that it led to this over 1,000,000% increase in mesothelioma, for example. But with sugar in this context, for folks to understand, here in our culture, on average, depending on which database you look at, we're talking about the average American consuming 70 to 130 pounds of added sugars a year. That's added sugars. It's not even the naturally occurring sugars in all of the different products and bread products and, grains and all those things. It is an insane amount of sugar that our genes, if we're talking about genetic mutations, have never associated before throughout our evolution. And so again, we're having these really strange conversations about it when something is so blatantly obvious. But as you mentioned, and I love this about your book so much, you go through and you acknowledge repeatedly how science like this, it takes so long. You basically have to prove, instead of you just already kind of coming into it, like, prove that sugar doesn't cause cancer. That should be where the work is at. It's very twisted. So, I think if you could add a little bit more just for folks to kind of to wrap up today and wrap up these insights, and just to provide a little bit more empowerment. We know that obesity is obviously a major, major component. You did some really great work putting some data together in the book, connecting obesity and cancer. Very, very eye-opening. But what are some of the other things that we can do to help to kind of modulate and create soil that is not conducive to cancer growth?
Yeah, I think that this is where the big opportunity for research lies, because there's actually not a lot of research with it. So I talk very briefly about chemoprevention, which is a term that was used sort of in the, starting in the 80s, and it's this idea that you can take something to prevent cancer. The truth is that after all these years, there's almost nothing that, and people have tried, like if I take this vitamin or this vitamin or this vitamin, maybe I'll prevent cancer. In fact, almost nothing does. So maybe in type 2 diabetics, this drug called metformin might, and maybe green tea might. Like there's some data coming out of Japan where they drink a lot of green tea where they say it prevents cancer. So that might be a chemopreventative agent, but it's iffy. The rest of it, all the vitamins, all the other natural supplements and this and that, there's actually no data whatsoever. But what's much more important is not what you're sort of eating, it's sort of what you're not eating, right? It's not that you need to eat more to prevent cancer, you need to eat less. And certain things are worse for you than others. Eating less sugar is a big one. Eating less refined food, eating less refined grains, because those are the foods, and we know this for sure. If you eat refined grains like muffins, which is made out of flour with a lot of sugar and other stuff, it's going to spike your insulin levels because of just the way it's made. So if you spike insulin levels, and insulin is a growth factor, well, that's going to, anything that promotes growth is going to be pro-cancer as well. So therefore, you want to avoid some of these things, such as the sugar, the refined grains. And that's just based on sort of knowledge, because if you can prevent obesity, and we know that if you eat a lot of sort of white bread and sugar, you're more likely to gain weight. I mean, that's sort of, most people have acknowledged that. And the other thing that's very interesting is this sort of ancient practice of fasting, because again, here's a practice which has been around for thousands of years. And what it does, of course, is it lowers all your sort of growth factors, because when you don't eat, your nutrient sensors, which is insulin, and also this molecule called mTOR, they're going to go down because you're not eating anything. So no nutrients are coming in, which sends the signal to the body that do not grow, because your body doesn't want to grow if there's no nutrients coming in. If you are sending this message to the body that says do not grow, that is going to be a soil that is not conducive to the growth of cancerous cells. And cancer grows faster than anything else. So the point is that you can actually do these things, such as eating sort of unrefined foods, fasting, and these are the same things that you see in a lot of traditional societies, as well as a lot of the societies that are, have low rates of cancer, like the sort of 1980s China and 1980s Japan and so on, where they're eating a lot less of things, but they're also incorporating these ideas of fasting. Like, they're not, like, people don't think you're crazy. Like, it's just part of what you do over there. And people here used to talk about it too, like it's a cleanse, it's a detox. So it's not that, we have it all wrong, because we have this idea that we want to take something to prevent cancer, when in fact you need to eliminate something to prevent cancer. And that's the more effective way to go. And it doesn't cost you any money, because of course, you don't have to buy whatever supplement they're selling. It's actually free. So these ideas of eating unrefined foods, cutting down the sugars, and fasting are probably the most important things if you want to do something about your risk of cancer today. And if you are able to lose weight, if you are able to reverse that type 2 diabetes, we know that obesity and type 2 diabetes are going to increase your risk of obesity-related cancers. So if you move yourself away from there, by low-carb diets, by eating unrefined foods, by fasting, you're very likely going to lower your risk of cancer. I don't know that for sure because the studies aren't done, but the problem is the time scale of those studies, that would take like a 15, 20-year study to do. By that time, it's, you can't implement it because that's so much later. But you can implement it today, because those are all parts of what we've done traditionally. So I think those are great things to do to lower your own risk of cancer for these things. And it all comes back to not the sort of genetics of it, but the sort of environment, the sort of the soil part of things. That's what we need to focus on, because that's what we can do something about right now.
Right. It's so powerful. And, again, it's one of those things where we should try to prove that fasting doesn't change the soil in a positive way, because it's kind of obvious on the surface if we look at, like you mentioned, mTOR, autophagy, all those benefits, enhanced immune system performance in some context, which is another one of those hallmarks, is the immune system not being able to take the cancer out. So just really creating a better environment for health to exist. Let's say that. So a soil that's more conducive to health rather than cancer. And so you talk about, you mentioned these tools. You've got a tremendous amount of work out there with the obesity code, the diabetes code, and now the new book right here, the cancer code, the most recent book. I know you've got something else up your sleeve coming soon, but this, and I shared this with you when we first connected, that I feel this should be mandatory reading for the public at large, but truly for folks who have cancer exposure in their life, where either they're diagnosed with cancer, somebody they care about, to get an underlying education that is so often left out of the context that we exist in right now. It's very much shrouded in mystery. It's so much experimental things without a lot of proof, and just giving people a new way of looking at things and feeling more empowered. So this book is incredible. And thank you so much for your brilliance and your time and energy going into something like this. And I know it's an adventure as well. Can you let folks know where they can pick up your book, and also where they can connect with you and learn more?
Yeah, so my books are available anywhere, so just check them out there. And you can also follow me on Twitter. My hashtag is at Dr. Jason Fung. You can also go to my website at thefastingmethod.com, and also check out my YouTube videos. Just look up my name, Jason Fung, and there's a lot there about weight loss, fasting, and that kind of thing. Not so much on cancer yet, but I'm releasing videos sort of every week, so I'll get to it eventually.
Awesome. Well, I appreciate you truly so much for putting this work together, and can't wait to see what you do next. Hey, if you like this video, make sure to check out this video right here to up-level your health today.
So if I say I'm depressed, I'm anxious, this is terrible, I don't know what to do, I'm so frustrated. As you do that, your brain and body and telomeres and everything, blood, homocysteine, inflammation, the whole lot's going crazy. But the minute I say, I feel depressed at the moment, I feel really bad, I'm having an awful day, but I can